Yes, can you hear me?
Yes, you can begin.
Okay, thank you. Good afternoon. It's a pleasure to present you this research paper carried out at the Military Institute of Engineering in Brazil. I am a dentist and master in material science from the Military Institute of Engineering. The work, entitled Influence of Grooves Orientation and Surface Finish on Fatigue Resistance of niti wires and endodontic instruments. This is a brief summary. Introduction. Machining of instruments provokes defects like grooves on its surface. This was the motivation for this study, the analysis of the influence of the ruggedness and its direction on the fatigue resistance of niti endodontic wires and instruments. Surface defects are stress concentration points for cracks nucleation. Literature results showed that the fatigue failures are more prevalent and unexpected due to the tensile and compression stress to which the instrument is subject during dental root canal preparation. So in this picture, there is an X-ray with two teeth, and it's possible see the curvature of root canals. The alternating movement inflection starts the nucleation of cracks in material. So what is the major factor in the life of the instrument? The direction of the grooves caused by cutting tools or the values of quantifying ruggedness? These are the objectives of this research: to compare the fatigue life of niti-orthodontic wires and related to orientation of defects observed by scanning electron microscope, ruggedness of the surface finish by optical interferometry. Compare the fatigue life of 4 brands in niti endodontic instruments and related orientation of defects observed by scanning electron microscope ruggedness of the surface finish by optical interferometry. Literature review about niti alloys. In 1988, niti alloy instruments for dental root treatment began to be manufactured. Niti rotary instruments have been widely used for root canal preparation due to better mechanical behavior, such as fatigue strength, flexibility, cutting efficiency, and canal centering ability, due to the superelasticity and shape memory properties of the alloy. Ruggedness. The several studies have demonstrated that the presence of grooves on the metal surface may decrease the number of the cycles to fatigue fracture of endodontic files. Furthermore, some studies have shown that these surface grooves on endodontic files may act as stress concentration points, decreasing their life to fatigue fracture. Cracks commonly initiated in the valleys on the surface grooves. This is followed by nucleation, growth, and propagation. Fracture mechanics. Fatigue fracture occurs unexpectedly and does not present plastic deformation at the fracture point. Fractures are classified into mode 1, 2, and 3. Fracture mode 1 is the type of fracture that occurs in the wires and instruments. Materials and methods. Preparations of the samples wires. The surface of the orthodontic wires were manually polished with silicon carbide sandpaper number 220. The samples were separated into 5 groups, each group with a different groove direction. Grooves were made in the following direction: longitudinal, 36, and 90 degrees. In the 5th group, samples without grooves were used. Each group had 15 samples that were divided into 3 subgroups for the rotation flexion test. The first subgroup was tested until it fractured. The second subgroup was tested at 50% of the mean fatigue time of the first subgroup. And the third subgroup was tested at 75% of the mean fatigue time of the first subgroup. The wires were tested in the rotary bending test. After the test, the samples were analyzed in the scanning electron microscope and the optical profilometer. Preparation of the sample instruments. Instrument samples, they were divided into 4 groups with 10 instruments of each trademark. The 10 samples were divided into 3 subgroups for the fatigue flexion test. The first subgroup with 5 samples was tested until they fractured, and the second subgroup with 3 samples was tested at the 50% of the mean fatigue time of the first subgroup. The third subgroup with 2 samples was tested at 75% of the mean fatigue time of the first subgroup. The instruments were tested in the fatigue bending test. After the test, the samples were observed in the scanning electron microscope and the optical profilometer. The morphology of the samples of wires and instruments was observed under a scanning electron microscope before performing the rotation bending test. After the bending and rotation test, the samples of wires and instruments were again analyzed in the scanning electron microscope. The average ruggedness and the valley depth of the samples were quantified in the profilometer. This picture shows instruments used in mechanical testing. Wave 1 gold, X1 blue, TDQA, and reciproc blue. To evaluate the mechanical behavior, wires and instruments were submitted to rotation fatigue tests. Testing was performed using a simulated stainless steel channel. The wires were tested in continuous rotation at a speed for 500 RPM until fracture. Subsequently, the instruments of each group were tested in reciprocal movement according to the manufacturer's instructions. The instrument is rotated clockwise and counterclockwise within the channel. Here we can see images from the wires as received, and it's possible to observe grooves and defects on the surface during the manufacturing process of the wire milling. It is possible to observe numerous grooves on the wire surface after the fatigue bending test. The cracks have a zigzag pattern, and it may be possible to observe the ductile type fracture surface. In the images of the samples of wires with grooves, it is observed the nucleation and propagation of cracks and direction of the grooves intentionally made in the samples. It's possible to observe the fracture surface with a ductile characteristics. On this slide, I highlight the wire sample with 60-degree grooves. In it was possible to have 2 distinct regions in the sample, with the grooves and with the cracks that follow the grooves, and the part of the sample without grooves, where the cracks present a zigzag pattern. This image is significant in demonstrating that nucleated cracks propagate in direction of the material's grooves. Endodontic files, especially those of smaller diameter, after manufacturing challenge and generally present surface defects and ruggedness resulting from the machining process. These defects on the working part of the instrument may be manifested as grooves, pits, and burrs. Grooves are observed as peaks and valleys on the working part surface of the majority of instruments evaluated by scanning electron microscope. Here, all the instruments from these pictures have surface defects. On this slide, we can see the angulation of the grooves produced by the manufacturers of the instruments. The angulation close to the 90 degrees and the 60 degrees. In the same way as observed in the wide samples, the cracks nucleated and propagated toward the instrument manufacturer grooves. After the tests, all instruments had a higher number of surface defects in relation to the state as received. The load induced during the tests provided nucleation, growth, and propagation of cracks. Both on the wires and on the tested instruments, it was possible to observe cracks in the direction of the grooves. Researchers such as Yilmaz and Uslu, they concluded that there is an increase in surface ruggedness after using the instrument. Both the ruggedness parameters, RA and valley depth of the wires and the files were quantified using a profilometer. In the table, it's possible to observe the difference in RA and valley depth values in samples without grooves. There is no statistical difference between the RA values of the samples with longitudinal grooves and the samples with 60-degree grooves. There was an inverse relationship between the values of RA with the fracture time, as can be seen in the table with the values of time until fracturing the test in rotation flexion. In this table are the RA values and valley depth of the instrument samples. There is no statistical difference between the RA values of X1 blue and TDQA. There was an inverse relationship between RA and valley values and fracture time. This table shows the fracture time of the wide samples tested in the rotatory bending test. As expected, the samples without grooves had the highest fatigue life, and samples with 90 grooves were expected to have a lower fatigue strength, as it was related to fracture mode 1, opening or traction, cracks nucleated in the area of the greatest bending of the wire or instrument curvature. But the 90-degree grooved specimens had the second longest time to fracture. This table shows the fracture time of the instrument samples tested in the rotatory bending test. There was an inverse relationship between RA and valley values and fracture time. The RA value alone should not be considered as a parameter to predict a shorter or longer time to fracture resistance. It is interesting to relate it to some other parameters, such as valley depth. Conclusions. The fatigue cracks nucleated in the superficial grooves and grow in the direction of the grooves, and the value of the ruggedness parameters, RA, and the valley depth are important factors in relation to the direction of the grooves. The instrument reciproc blue presents better resistance to fatigue in rotation flexion when activated in the reciproc all movement, and presents lower values of ruggedness, RA, and depth of valley in relation to the other instruments studied. Statistical analysis, ANOVA and Tucky tests performed for the RA ruggedness and validef analysis of the wireless endodontic instruments demonstrated that the 30 G-wireless samples and the Wave 1 Gold instrument samples have the most severe surface defects in their sample group. The instrument reciproc blue have a greater fatigue resistance than the other instrument tested, with a significant difference in time to fracture compared to the other samples. Tucky's test indicated that wires with groups at 30 degrees in relation to wire length have the lowest fatigue resistance compared to the others. Tucky's test showed that there is no significant difference in fatigue fracture time between the Wave 1 Gold, X1 Blue, and TDQA instruments. This slide is the end of my presentation. We are grateful for the financial support of the Brazilian Ministry of Science and Technology. And thank you so much for your